This is the story of how very little things like this or this can cause things to go horribly wrong. But let's start from the beginning. Hello and welcome back to Noel's RetroLab. This is not the video I set out to make at the start. I was planning a general restoration of this Dragon 64 to fit with Zipped Handy, but halfway through I turned on the computer and this happened. I thought that maybe it would be an easy fix, but as I started looking into it, it was clear that it was something running pretty deep into the video generating circuitry. So I thought, what would you prefer that I focus on? Me trying to tape the box together or going into a video circuit deep dive? Yeah, that's what I thought. Before we get started, and since this is the first time I'm featuring the Dragon computer in this channel, let's have a look around the Dragon board itself to get oriented. That will help us later on with any diagnostics. The Dragon board is neatly separated in two sections. On the top is the voltage generation half, which also has a video connector, and the bottom is the main board. Incidentally, they can be separated with a really nice and sturdy connector that makes them a pleasure to work with. Take that, Spectra Video! Let's focus on the main board, which, by the way, has a completely different layout than the Dragon 32, so don't use this when you're looking at a Dragon 32. Right there, we have the CPU, which is a 6809. It's closely related to the better-known CPUs like the 6502 and the 6510, so if you're familiar with those, you'll feel right at home here. Incidentally, I was forced to learn 6809 assembly for a tough repair years ago involving modifying the system ROM. And coming mostly from a Z80 background, I found some of the addressing modes mind-bendingly awesome. Right at the bottom, we have 64 kilobytes of RAM in the form of 8 4164 DRAMs, and right up there we have two 16 kilobyte ROMs, all very standard stuff so far. Next, we have the VDG or Video Display Generator, which generates the video signal in the format of YUV, just like the ZX Spectrum ULA. Over there we have the SAM, which stands for Synchronous Address Multiplexer, and it's like the traffic controller of the whole computer, coordinating the CPU and the VDG memory requests. At the bottom we have a chip dedicated to asynchronous serial communication, and the big crystal on top is a UART oscillator. Over on the lower left corner we have two PIAs for parallel communication, keyboard scanning and all of that. And then that whole mess over there is roughly in charge of converting the YUV video signal into the composite signal. We'll be living there for most of this video. I wanted to thank PCBWay for sponsoring this episode. It would be great if someone did a replica board of a Dragon PCB and we could get it printed on PCBWay. I know the quality would be great as usual, but most importantly, the new board would not have a fatal flaw that this PCB has, and that will come and hunt me towards the end of this episode. Can you spot the problem? So again, this is the image we get when we turn the computer on. It should have a green background with black letters and a black border, so clearly there's something very, very wrong. Let's start looking at the video signal at the source, at the VDG itself. The VDG generates three video signals, a luminance signal and two chroma signals. Let's start with the luminance signal, or also called Y, first. And yeah, that looks about right for a mostly solid color screen. The two signals related to color are red minus luminance, or R minus Y, and blue minus luminance. If you want a refresher on that, I have a more in-depth video about it that I'm putting a link in the corner. So R minus Y looks pretty reasonable, and B minus 1 too, so without digging deeper, they seem to be about what you'd expect. The video signal circuit is rather large and intimidating initially, and in part is because the video display generator, the 6847, isn't really prepared for PAL signals, so half of the components in the circuit are massaging the video so it can be PAL compatible. I'm not going to go into the details yet, but let's have a look at the basic idea. The three video signals Y, R minus Y, and B minus Y come straight from the VDG on the left of the diagram. The two chrome signals are slightly modified and fed into the LM1889 chip, which will encode the color signal into a 4.4336 MHz carrier wave. That's the same encoder chip found in the ZX Spectrum. The luminance signal is then combined with this chroma signal, amplified, and the result is the composite video signal itself. There are many more details, but those are the rough steps. Along the way, there are two knobs we can adjust. There's an adjustable resistor, VR1, which changes the offset of the whole signal before it's amplified. Then there's also the adjustable capacitor C32, which is associated with a high-frequency signal used to encode the color. I believe the capacitor will slightly change the signal frequency. So those might be good starting points to see if we can improve things. Let's start by tweaking the resistor with the bias level. And no changes. Oh, except that we lose the signal completely. And no changes the other way either. And what about changing the clock frequency? No, that seems to have even less of an effect. Since the LCD is sometimes quite picky about video signals, let's try it on the CRT, which is my retro display anyway, so that's where I really want to display it. Okay, that looks different. And tweaking the bias level, oh wow, that looks just about right. And if we go all the way to the other end, nope, we lose the image there, and it gets blue. Interesting. So one thing I noticed is that even in the lowest setting I could set it to, the image is still very bright and a bit overblown, which is very odd. Since this is in charge of biasing the composite signal itself before it gets amplified through a few transistors and such, I thought I would start looking in here. And one of the things I found right away is that this resistor, this variable resistor, is hooked up to the composite signal line in one end, so that's why it biases it. And the other end is not connected straight to ground, but it goes through a link. Right here, it is connected to link 2 right there in the middle. And we have an option apparently. If we put this link here, link 2 would be connected straight into ground, which is the normal configuration for these guys. If it's connected to the top like it is now, then the variable resistor is connected to 2 diodes and then to ground. And what's the point of that? It's just to increase the voltage because each of the diodes has a voltage drop through them. So this could be, probably almost one volt in there. And that would for sure affect the bias of the signal. So what I did is I put a pin header, and that way we can select which configuration we want. And so initially I'm going to put it back the way it was, connecting the variable resistor to the diodes. So when I turn this on, this looks like a very normal kind of composite video signal with the color burst, the back porch, and then the luma, the information plus the color encoded in that higher frequency wave. When I tweak the variable resistor, the signal is just a bias and it moves up and down. So below this, it probably stops being a valid video signal anymore because we're just compressing that too much. So that's probably fine. And then this goes to about there. So we have very little range that we can really modify this and still be a valid video signal. It doesn't go up any further than that. So I'm going to put it back in there. And now I'm going to turn it off just in case. I'm going to switch over to bypassing the 2 diodes and going directly to ground. And we should have much more range. So this is similar. Once we start going down, it probably soon stops being a valid composite video signal. But we can go further up and it looks totally fine. And that looks the same as before. So I'm going to adjust the resistor. Oh, and it's getting, oh, look at that. Okay, so this is as low as it gets, and this is way darker than before. So clearly that's probably not what you want either. You probably want something more like that. And this maybe will actually look okay on the LCD. Oh, still blue. And if we adjust this, do we get... Nope, nothing over there. And nothing over there. I still think this is the right thing to do because it looked much better on the CRT TV, but it's not solving our blue chroma problem. Everything is working fine with a CRT TV, which is my primary target display. I had read that the PAL signal generated by the Dragon is a bit peculiar, so maybe the CRT is a little bit more lax in what it accepts and the LCD more strict. I could have called it quits in there, started on the box restoration and moved on to the easy stuff. But that's not what we're here for, is it? I kept thinking that maybe there is something really wrong with the video signal, and if so, I should at least give it a good go before chalking it up to an unusual signal. I checked just about everything involved in the color circuit that takes care of generating the encoded color signal, and I couldn't find anything obviously wrong with it. But since the problem seems to be squarely in the color encoder, the obvious suspect is the LM1889 encoder chip, so let's swap it out for a working one and see if that improves things. Okay, let's try with this other LM1889 that I know it's working correctly. And nothing. So there's one more test I want to do, and it's to see what kind of video image we get without this chip at all. So this should simply not generate any chroma information in the composite video signal. So we should just get the luminance. And that looks pretty good to me. Looks nice and sharp. No weird lines over there, no lines crossing like that. So yeah, whatever problems we're having is very specifically with the chroma subsignal. Just to make really sure, I adjusted the frequency of the chroma carrier to be exactly 4.433619, well, 2 because I ran out of digits, megahertz, and nothing. Things were still blue. And then this started happening. I would turn on the computer after it was off for a while, and the screen would start doing all sorts of weird things. It would start out one color, lose the signal, come back as that blue screen, then start getting some kind of weird color bars, and eventually settle on some really washed out colors. Just in case there was any doubt before, now it was clear that the color circuit was really messed up. So I redoubled my efforts. I thought that the color instability could be due to slightly damaged tantalum caps. I know they're self-healing, so I thought it may have something to do with that. I didn't have any tantalum capacitors on hand, so I replaced them with equivalent electrolytic capacitors, and nothing. Then I thought that maybe the problem was that it was overheating after a few seconds, so to test that theory, I applied cold spray all over the video circuit, and nothing. And just out of desperation, I socketed the op-amp involved in the chroma signal processing, replaced it with a working one, and nothing. Yikes. Okay, at this point I was annoyed. All my obvious checks failed and I had made no progress, and at the same time it was clear that there was something seriously wrong with this dragon. So what's the solution? To dig even deeper, of course. So buckle up, we're going for a wild ride and it's going to get choppy out there. You knew this was coming. Time to dig into the full video circuit. We've already decided that the luminance is working fine, but I wanted to talk about that for just a second. Remember how I said that the VDG isn't really prepared for a PAL video signal? The VDG generates a signal with 524 total lines, which is close to the NTSC standard, so that extra circuitry you see here actually pauses the clock into the VDG twice per frame and generates extra blank lines to match the resolution of the PAL video signal. It feels like a total hack, but hey, that's what you need to do when you're using mostly off-the-shelf components. Having said that, let's forget about the luminance path and focus on the chroma signals. I mentioned earlier that the R-Y and B-Y signals generated by the VDG are processed a little bit and then fed into the encoder. So what exactly is going on in there? B-1 is actually sent directly into the LM1889 encoder, but R-Y goes through a few steps. This is the R-Y signal. Each of those squarish waves is a line on the display. It actually looks pretty noisy, but we're also at a pretty low voltage resolution. I actually don't know what's that big dip in the middle. Maybe it's the cursor and the trigger of the oscilloscope is catching that particular line, but that's not really important right now. The middle section is an inverting op-amp, the one that actually I already desoldered and tested earlier, and we know it's working. So here we can put the input of the op-amp in one channel, yellow, and the output on another one, blue, and we can see that they're always perfectly inverted. The last block is a multiplexer, either selecting the regular R-Y signal or the inverted one that came from the op-amp. That's because for a PAL video signal, the color phase is reversed every other line. So on one line, it sends the regular chroma signal, and on the next one, it sends the inverted one. So if we put the R minus Y on one channel, and on the other channel, we put the output of the multiplexer, we should see that half the times the signals coincide, and half the time they're inverted. And it sure looks like they're inverted all the time. We're definitely onto something here. So let's have a look at the signal that selects whether to use the normal or the inverted chroma. It should be on for one full line and off for the next line. And this is what we get, which is clearly wrong. Those are pulses at the beginning of each line, but the signal isn't being held for that duration. So, things are starting to make sense. Okay, let's pull a bit more on this thread. Where is that selection signal coming from? It's coming from IC30, which is a 74LS74 flip-flop, and it's set up in a very common configuration with the negative output connected to the input. So anytime it detects a positive edge transition on the clock signal, it negates its state. So this is the clock signal going into the flip-flop, and that seems fine. I'm imagining that's exactly the horizontal sync signal. But this is the output. Instead of flipping the state and staying flipped, it looks like it just follows the same level as the clock signal itself. So we're not selecting the right chroma every other line. No wonder the color was really messed up. So it's pretty clear that the flip-flop is faulty and we should just go ahead and replace it. Incidentally, this is really uncanny because quite a while ago I had a video fixing the color on a PAL Apple IIe, and I'm putting a link in the corner right now, and that came down to exactly this same problem, a faulty 74LS74 that prevented the chroma phase from alternating. Alright, with the flip-flop socketed and replaced, let's try that again. This is the clock pulse into the flip-flop. And this is the output, but this is the same as before. That's not what I was expecting at all. What's going on in here? To understand this, we need to zoom in some more into the clock pulse. And look at that. As the pulse transitions down, it bounces and rings. And some of that is normal, but this is clearly excessive, and it's triggering the flip-flop again because there's another rising edge. That's why the state of the flip-flop was only flipping for the duration of the clock signal itself. The clock pulse is generated by a 74LS123 chip. This chip generates a pulse of a certain length whenever it detects a rising edge. The pulse length itself is controlled by an external RC circuit hooked up to a couple of its pins. In this particular case, it's configured to generate a 3 microsecond pulse at every horizontal sync. I wonder if there's a way to fix that bouncing or whether the chip needs to be replaced completely. So I tried a variety of things. I added a capacitor on the output and that didn't work. I tried adding an extra decoupling capacitor closer, made no difference. And I even changed the capacitor that controls the interval and it also made no difference. So at this point, I'm really left thinking that something went wrong with this particular chip and we need to put another one. So I'm going to take this one out and take it out of another Dragon and see if that fixes things. And if so, I'll just go ahead and order a few of those. I did replace the 74LS123. I went to turn the computer on and nothing was working. It was one of those curses of repairs that happens sometimes. I didn't even film it because I thought it was something uninteresting that I had accidentally done. But it turns out it was quite interesting, even if it was unrelated. And I eventually tracked it down to D5, the output of this DRAM, that it was always high. So it was always tied to 5 volts. And I thought it was the DRAM chip, so I replaced it, and that wasn't it. So then I thought it would be one of these 2 latches, buffers thing. I removed them, didn't even socket this one yet, nothing. We're still getting the connection to 5 volts. That happened right after I socketed IC31, which is the 74LS123, and I just kept checking, make sure that I didn't short anything and I didn't see anything. I was just going crazy until I realized that the line that is actually shorted to 5 volts it doesn't go all over the board. It actually just connects this chip, and this pin here. Nothing else as far as I know. And guess what? That track goes right under the socket I installed. And This is one of those boards like the TI-99 4A that doesn't put solder mask on tracks in between the eyelets, the vias of a chip. So I think, even though you really can't tell here, and I got really close to it and I can't even tell it, I think there's a short in here. Let's actually look with a microscope. So this is actually the first time I'm taking out this microscope. Just full disclosure, it was sent to me for free by Star. They're the makers of this microscope, and I think they had seen maybe my review of other microscopes and magnifying glasses, and they wanted me to have a look at this one, no strings attached. I haven't tried it yet. This is going to be the first time that we're going to do this together. So right away, I can tell you one thing that I love compared to the other one, and it's a silly thing, but it's having those lights on the sides. Having the lights directly from above kind of kills all detail in there. So that right away, and the fact that they're adjustable, is great. It's also much bigger, and I think the quality of the screen is better. So let's give this a try. Also, because this platform is bigger, I can put a whole board like this, and it works really well. So let's see. Let's find our spot. We may be seeing something there. I'm gonna zoom in. There's a little sliver. I'm not sure that's a short or not. Let's try zooming way in. Okay, that's about as zoomed in as I get. Okay, that might be too zoomed in to get a sharp oh, there you go. Look at that. Look at that. That right there is the nasty little short that happened under the socket. So yeah, tracking that down was not fun at all. Let's try to fix that right on the microscope. Wow, the soldering tip is huge. There you go, that's it. I think we don't have the short anymore. There it is. I might try to get that last little bit to prevent any shorts later. There we go. That's better. So let's see if we still have a short between data out and 5 volts and nothing. So it should be connected here. Yup, and here. Yup. But not to there. And it should be right there. Yes. That's something to watch out for in these boards without the solder mask along those tracks. So with all the chips back in, let's go ahead and start checking the output of the 74LS123, which is right here, and that looks really good. Yep, there's barely some ringing there, nothing enough to trigger the double edge detection like it did before. So that's really good news. Now let's see if we can see the wave being inverted sometimes and not the other times. That was what first led us to this point. We see that sometimes they are inverted, like right there, and then right here they're the same. It goes down, and then it goes up, and then again this goes down, but then when this goes down it goes up. So it is definitely sometimes it's inverted and sometimes it's not. So this seems to be working correctly, and the way to test for real is let's have a look at the screen. All right, let's do this. I have a good feeling about this. Oh, check it out. Perfect green. It's actually a little over bright, I think. So now this is time to tweak those parameters a little bit more. So this was the offset, which controlled the overall brightness. There you go. Oh, that is so much better. So I think we finally fixed the color issues on this dragon. It's, again, a green dragon. This is a really simple, basic program to test the colors that I got from Michael Dornbos. And let's see what it looks like. There we go. Perfect. We get all the different colors that the dragon can produce and everything. So, and this is even on the LCD. On the CRT, I'm sure it looks way better. Actually, let's go look at it in the CRT right now. And there you go. It also looks great on the CRT. I'd say yes, this was a very successful repair. Incidentally, the working 74LS123 came out of a Dragon 32, and just for kicks, I put the faulted chip in the Dragon 32 itself and tested it, and it actually works fine. I'm thinking the IC is just borderline faulty and generates more bounce than usual, but the Dragon 32 actually has the RC circuit that controls the pulse duration very close to the chip, as it's supposed to be, as opposed to the Dragon 64, which has it quite far away from the chip itself. So that might be enough for it to work correctly. Now, this is making me wonder if this Dragon 64 ever output color correctly, or if it came this way from the factory. Wow, that was a subtle fault that caused all those issues with the color signal. I probably should have started analyzing the signal earlier instead of messing around changing the encoder and the capacitors and all of that, but it felt like the easy thing to do at the time. Oh well, lesson learned. Anyway, I hope you enjoyed that episode as much as I did making it. Leave me any comments below, and I'll see you next time. If you enjoyed this video, please consider supporting Noel's Retro Lab on Patreon or joining the membership on YouTube. Not only is that the best way to support this channel and allow me to continue making more videos, but you also get some extra perks like early access, ad-free videos, and more. Thank you again to all the supporters. See you next time.